The lesson topic for this video is binomial probability. As it says in the definition, a binomial experiment means that there are two mutually exclusive outcomes that are referred to as success and failure. Now let me remind you that mutually exclusive means they do not overlap. Okay? So these experiments that have either success or failure as the outcomes come from Bernoulli, Jacob Bernoulli, and just a little information about him there. He was Swiss. But anyways, some examples of these then Bernoulli trials or binomial types of trials means that we could either flip a coin as an experiment, and then heads could be success, which means tails is failure. And those are the only two outcomes possible. Rolling a die, and we could say 3 is success and anything else is failure. So 1, 2, 4, 5, and 6. Voting for candidate A is success, but anybody else that you vote for is failure. Determining eye color, green is success. Or spraying crops, the insects are killed, is success, and anything else would be failure. So that's just a little introduction to what binomial probability is all about. In our first example, we're going to figure out if I roll a die 3 times, what is the probability that I'm going to get a 6 exactly 1 time out of those 3 rolls? So a 6 in this case is going to be success, and of course anything other than a 6 would mean failure. Now if I'm going to roll a die 3 times, okay, 1, 2, 3, could I get a 6 on the first try? Sure, I could, right? Then what would I need to get the second try and the third try if my goal is to find the probability that I get a 6 exactly 1 time? Well, I'd have to get anything other than 6. So let's call this not a 6 and not a 6. Right? So what is the probability that in our first roll we get a 6? Well, there's 1 6 on a die out of 6. What's the probability that on my second roll I get not a 6? Well, that's a 1, 2, 3, 4, or 5 out of 6. And again, not a 6 again would be 5 out of 6 again. Okay? Now, just a reminder, these are independent events. Your second roll does not have any, is not impacted at all by your first roll, right? So then if we multiply these, we would get the probability 25 out of 6 times 6 times 6, which is 216. But that's not our answer. And the reason that's not our answer is because that's not the only way it could happen that I get a 6 exactly 1 time. I could also get a 6 second. I could get the 6 here. So that means there's another way it could happen. So then I would have not a 6 here and not a 6 here. But that's not the only way it could happen. It could also happen that I get the 6 the third time, and then not a 6 and not a 6 the first 2 rolls. So what I'm saying here is that we could get a 6 1 time this way, or we could get a 6 1 time this way, or we could get a 6 1 time this way. So what does that mean we have to do? It means we have to add 3 different situations up, the probabilities. And then what's going to happen for each of these, the fraction, what's the probability of not getting a 6? Well, we already said that's 5 out of 6. And then a 1 out of 6 for getting a 6. And then not a 6, well, there's 5 ways out of 6 to not get a 6. And then same thing over here again, 5 out of 6 times 5 out of 6 times 1 out of 6. So each and every one of these is going to be 25 out of 216. They're actually multiplying the exact same fractions, just in a different order. So 25 plus 25 plus 25 is 75 over, keep the denominator, we're adding fractions, 216. Now, there's a shortcut to this process, and I'm going to show you the exact same example on the next screen using that binomial experiment shortcut. So here's the same problem. So the way we can do this, a little shortcut here, I'm just going to show you the formula. Sorry, I can't quite talk here. I'm going to show you the formula. I'm going to talk you through it. Okay? First of all, we are going to use a combination. Okay? Combination means that the order in which this happens doesn't matter, right? Or is not involved. I'm going to talk to you about that a little bit more in a second. Since we're rolling the die 3 times, that's going to go in front of the C. And since in this binomial experiment we want to get a 6, a certain success, exactly 1 time, we're going to put a 1 right there. Now let's talk about what that tells us. That tells us the number of different ways that you can get that 1 6 when you roll the die 3 times. Remember when we did this on the previous screen, I said, okay, the 6 could be here, and then not 6, and then not 6. And how many different ways could that happen? Well, the 6 could either be the first roll, or the second roll, or the third roll. So that's what this computes. It tells us that if we're going to roll the die 3 times, and we want a 6 exactly once, this will compute out to be, and now if you think about it, there were 3 different things like this that I wrote down, right? So this actually does compute to be 3. 3C1 is 3. And the reason it's a combination and not a permutation, which by the way will always be a combination, is because the order in which we list this option versus the other 2 options does not matter. It's not important. Okay? So now the next thing we're going to do is we're going to take how many different ways it can happen that a 6 is rolled 1 time, and we're going to multiply it by the probability of getting a 6. So the probability of getting a 6 is 1 out of 6. And again, how many times do we want that 6 to be rolled? Once. And then the other 2 rolls, right? The other 2 rolls, we want them to be not a 6. So we're going to find the probability of something not being a 6, which is 5 out of 6, and we're going to raise that to the second power because we want 2 rolls to be not a 6. 2 of them. So 1 roll we want to be a 6, and that's 1 out of 6 chances, and 2 rolls we want to get not a 6, which is 5 out of 6 chances. So you could just enter this whole thing right here into your calculator. Make sure to put multiplication symbols in between like that. Or you could simplify it and then compute it. But I just want to show you how this does work out to be the exact same answer as we had on the previous slide. What's 1/6? Because we already have 3C1 is 3. You can compute that. Then we have 1/6 to the first power. Well, that's 1/6. And then we have 5/6 to the second power. Well, that means we square both the numerator and the denominator, which gives us 25 over 36. We can make this into a fraction as well and just multiply the numerators. 3 times 1 times 25 is 75. And multiply the denominators. 1 times 6 times 36, which is 216. So we end up with the exact same result using our formula right here. If you are interested, I just added in some information on what each thing calculates. Again, the 3C1 right here finds the number of ways you can roll a 6 once out of 3 rolls. So there's the 1 and the 3 in that, once out of 3 rolls. Next, we've got the probability right here of rolling a 6, 1 out of 6. And here we've got the probability of rolling something other than 6. So 1, 2, 3, 4, or 5. Up here we've got the number of times we want, quote unquote, want to roll a 6. Again, wanting meaning in the problem, which is 1, exactly 1 time. And the number of times we want to roll something other than 6 goes there. Let's try another example. This example says Johnny is a 73% free throw shooter. That means he makes 73 shots out of every 100 he takes. In Friday's game, he shot 4 free throws. What is the probability that he made exactly 1 of them, or 2 of them, or 3 of them, etc.? So let's try this first one. We know we need to use a C situation here, because I told you it's always going to be a combination. How many free throws is he shooting? He's shooting 4. How many of them do we want him to make? okay, in the problem. Of course, we want him to make them all if he plays for Osseo, right? But it means that we want him to make exactly one of them, so we put a C, 1 after the C. Okay. Now, next is coming the probability that he makes it. He makes that one. Probability of success. Well, he makes 73% of the shots he takes. So, 0.73 is the probability he's going to make a free throw. And we've got to raise that to the number of free throws that he wants to make, or we want him to make in this problem, which is 1. Okay? And then we need to multiply that by the probability that he misses. Well, let's think for a minute. If he makes 73% of his free throws, what percentage does he miss? Well, 27. Pardon me, because 73 plus 27 is 100%. So 0.27 is the probability he's going to miss, and we want him in this probability question to miss 3 of them. Notice every time you do one of these binomial probabilities, the exponents here will always add up to the total number of things happening. So 4 free throws in this example. 1 of them we want him to make, 3 of them we want him to miss in this probability question. Now all you need to do is compute this on your calculator to find the answer. I've included now here up at the top the way that it looks on the TI anyways. It's going to be very similar on the Casio calculator. You get your 4C1 times 0.73 raised to the first power times 0.27 raised to the third power. So in this case, the answer here is 0.057. Let's round to 3 decimal places, please. The thousandths place is our probability. Now, why is this so small of a probability? Well, because if he's a 73% free throw shooter, he's probably not going to only make 1. This is unlikely. He should make more because he usually makes about 3 out of every 4. So if we did 3 of them, our probability is going to be a little higher. All right, let's do that one. Let's skip the 2 for now and just do one more problem here. So if we want him, Johnny, to make 3 of them, so he's got 4 shots he's going to take, and we want him to make 3 of them. In any order, we don't care what order he makes the 3 out of 4. Times that by, again, the 73% likelihood of him making it, raised to, just checking to see if you could fill that in, raised to the third power, because we wanted to make 3 of them, times 0.27, the probability that he's going to miss, and how many do we want him to miss? Well, the remaining 1 shot that he didn't make. This time, it's way more likely. It's 0.420. So about 42% chance that he will make 3 out of his 4 free throws in Friday's game. Because I'm running out of time on my video, I want to just go through this one really quick. You take a 10-question multiple choice test on which each question has 4 choices. If you randomly guess on each question, what's the probability that you get 5 of them correct? First of all, 10C, how many do we want correct? 5. Okay, we're going to multiply that by the probability of guessing correctly, and we want that raised to the 5th, times the probability that we answer incorrectly, also raised to the 5th, because if we want 5 of them correct, we would want 5 of them also to be wrong. What is the probability that we guess correct? This is a tricky one for some people. If there's 4 choices on a multiple choice test, A, B, C, and D, what's the probability that you guess the right answer? Well, it's 1 answer out of 4 choices. What's the probability that you guessed wrong then? 3 chances out of 4. And that's how we would compute this one.